Okay, with standing waves, I think you've seen just the basic intro to standing waves. What I want to do is just look at the maths of not the maths of the actual standing wave itself, but just the maths of waves on a string. We already sort of did that when we said, okay, you got the first one looks like that, the second one has got 2, and the third one's got 3 half wavelengths in. So for the standing waves on between these 2 points, and remember that's a node, depends on the harmonic where the antinodes would be. But with strings, that's an antinode at each end. Then the formula we get, actually this looks like crap, let's just make sure. So that would be the second harmonic, right? And that would be your antinode, and you'd have a node in the middle. So this is the second harmonic. And this is where you are basically saying n half wavelengths equals L, L being the distance between the 2 points. So with that sort of information, you can say that the wavelength is equal to 2L, bring that one up there, divided by n. And that's for n equals 1, 2, 3, 4. Alright, so if that's your wavelength, you can see that your frequency is equal to velocity over wavelength, which would be the velocity over the wavelength, which is 2L divided by n, so times by n. So that's where we get the fact that the frequency increases n equals 1, n equals 2, n equals 3. So if your frequency starts off at 100 for harmonic 1, it's 200 for harmonic 2, 300 for harmonic 3, 400 for harmonic for harmonic 4, and it's really quite straightforward. Now, the formula for an open tube, see if you get an open tube, and hopefully we'll show you this in class, is exactly the same, but drawing them isn't, because when you've got one like this, instead of having a node at each end, you're going to have an antinode at each end with an open tube. So the first harmonic, if you're going to have an antinode, that means it can swing maximum. It's not going to be in the middle of the end. So it can swing like that. So at the other end, what could you have there? You've got to have your node in the middle. So basically, to get an antinode at both ends, you've got to have a node in the middle, right? And that's your first harmonic, right? Could you have done it any more simply? That's always a good question to ask. But if I'd gone like this, with my antinode maximum swing up there, the only way I could have done that would be to make a quarter wavelength, right? But that doesn't work because this is not a node. So you must start with half a wavelength. Now, the second one, you're saying, okay, well, what's one wavelength? One wavelength means you get back to where you started, right? And after half a wavelength, all right, then you're exactly halfway out of phase. So basically, this one is one where you go like that, all right? You've got the half wavelength, so this one is wavelength equals L. This first one was where wavelength over 2 equals L. So you can see it's the same formula. In this case, this becomes an antinode, this becomes an antinode, and the nodes are sort of in between. All right, so the open tube is similar in formula, but different when you actually draw it. Now, this is the way we express, remember, and I think from year 11 I stress this again and again, where I say, what you must do is remember that the actual particles in a tube are a longitudinal wave, so they're moving backwards and forwards. So what this type of graph means is not that the particles end up being up here. The fact that we've got that maximum displacement from the equilibrium, we're using a transverse wave to display a longitudinal wave, which is really silly. All that means is, when we say there's an antinode there, is that the particles in the end there do maximum oscillation left and right. The particles here do minimum oscillation left and right. Particles here, maximum, minimum, maximum. These are nodes and antinodes. We'll do a bit more, obviously, of drawing those in class. Now, the closed tube is the one that's a little bit different. The maths for the closed tube. Now, with the closed tube, you've got one end closed. Before I actually move on to that, this open tube, hard to explain how the standing wave is created at the end of the tube. How do you get an antinode there? Okay, and I think, well, not so much the antinode, we can sort of understand that, but how do you get reflection? Remember, a standing wave means we've got two waves traveling in opposite directions. You can understand how you could have maximum movement here, but how do you get reflection? Why does a wave not just travel out of the tube and never come back? How do you get a standing wave in an open tube? Watch the little video on that and I'll try and explain it. Alright, closed tube. In this case, this must be a node. How can you get maximum left and right movement there if you've got a wall in the way? Well, you can't, but you can here. So we immediately know that must be an antinode. So we can say, oh, I can fit a quarter wavelength in there. So for the first harmonic, I can say quarter wavelength equals L. L being the length of the instrument you're looking at. Nice. But what's the next one? If that's a node, and that's got to be an antinode, can I sort of fit a half wavelength? No, because a half wavelength is going to be 180 degrees out of phase, which means it would have to be at the bottom. It can't be like that. So the next bit that we can actually do, so if this starts here, it must end up here. So we sort of would end up like that. All right. So this becomes node, antinode, node, antinode. All right. And that's obviously 3/4 of a wavelength. So we've got a different formula here, haven't we? What you've still got half wavelength differences. This is again first harmonic, but this is, we missed out one. This is not second harmonic, if you like. What we find with the closed tube is that we've got a nice one, but we have to go with quarter wavelengths now. And so we say n wavelengths over quarter equals L, but only for n equals 1, 2, 3, sorry, 1, 3, 5, odd numbers, right? Because that gives you the half wavelength differences. So that's how that one works. And so you don't actually get the second harmonic. You jump straight to the third harmonic. You can do the calculations. If we work out, well, let's work out a formula for the frequency here. If we do the frequency formula for the closed tube, let's see what it tells us. It tells us we've got n wavelengths over 4 equals L. That's L. So 4L over n equals wavelength. Let's put that into our formula. V divided by wavelength equals frequency. So V divided by this wavelength here is 4L over n equals the frequency. Now what that tells you is that the first harmonic is going to be a certain frequency, and the third harmonic is 3 times as big, and the fifth harmonic is 5 times as big. So you lose the second and fourth and sixth, you lose the even harmonics with a closed tube. So closed tube is the interesting one. All right, that's all I think we need to do on the simple maths for standing waves.